Think about this. We are the culmination of 14 billion years of an unbroken cosmic evolution. And if this is true, it means that we are the universe trying to understand itself. Are time and space even possible to imagine on this scale? Let's find out. Hey guys, this is Rich, and welcome to Let's Find Out. Tonight we're going to be exploring the concept of scale in the universe, and we're going to be doing it by looking at our solar system, and not just the sizes of the planets and the sun, but the truly colossal distances between them. And we're taking a long journey this evening, so grab a snack or a drink, or just relax and get comfortable. And hopefully next time you're outside looking at the stars at night, you'll be able to better recognize that what you're actually seeing is suns hundreds, maybe even thousands of light years away. And maybe this will help us have a slightly deeper sense of and appreciation for just how vast this beautiful existence really is. The other day I was trying to sketch out a slightly more accurate representation of the Earth-Moon system, particularly in regards to using parallax to determine the distance to the moon using trigonometry. Essentially, you just draw a right triangle and you figure out the angles inside it, which gives you the side length. The concept of parallax, though, is so often misrepresented, mostly just in terms of scale. I mean, just like any popularizations of space, astronomy topics, whether it's on the History Channel or Discovery Channel, whatever, or even other YouTube channels. And so I was drawing it out just because I personally didn't understand it. I was in awe. Absolutely, I was really just impressed by how the heck we could know the distance to the moon just by looking at it and using some mathematics and basic math at that. Not even very, we're not getting into calculus and quantum mechanics there. Relatively basic mathematics, just using a right triangle. And it's so often misrepresented. So if we have the Earth there, the moon there, and then three, just a very simple image of a, constellation representation of distant stars. Let's see, let's get this out. Let's get our concept of parallax is that when you measure from, you observe the moon, I guess we'll go right next to it, from one position on Earth, and then you travel a distance away to another position on Earth, the moon will look like its apparent position in the sky has changed. And you need something much more distant than the moon to measure the change in position against. The fundamental concept is that, so from this position, right here, the moon against the sky would look like this. And then from this position over here, at the exact same moment, mind you, so you would have to synchronize with someone else. Say this is Paris, France, right here, and this is Greece, Athens, Greece, maybe. The moon over here in Greece would look like it's right here. And the concept of parallax, the fundamental concept is that these stars have to be so far away as to practically be considered infinitely far away. And by doing that, what that allows us to assume is that the light rays from the stars hitting the Earth are essentially parallel. And what that allows us to do is the mathematical concept of two parallel lines being transversed. I should have drew them a little bit further apart, but the transversal of two parallel lines, two lines that are equidistant apart along the infinite length of them. Two lines that will never meet. As one math site joked, I got a kick out of. Parallel lines have so much in common. It's a shame they'll never meet. It's a shame they'll never meet. I thought that was funny. A transverse of two parallel lines. So this, for our case of parallax, would be the rays of light coming from the same star hitting the Earth, and it's so far away that the rays are considered parallel, even from both of these positions. And the transverse means that allows us to determine our little triangle. And the whole point is here, it's to make a right triangle so that we can figure out one of these legs. And that would be the distance from the Earth to the moon. And when we look at these stars from the first position, we want to draw a line like we did right past the moon. So there's a reference point, and that'll be, let's say, this star right here. That star right there, let's spell the word right, it's going to be our, oh boy, reference star. My little pen was getting caught up there. And we're going to look at that and use that as our standard of our static background, essentially, against which the apparent position of the moon has changed. So when we look at it, the moon from this point on the Earth right now, remember Greece, we'll say that's France, and that's Athens. Now these light rays are essentially parallel from the stars. And if we look at the moon from Athens, our second position, we need to observe and recognize how much it has changed position relative to our reference star. And this change in position here, or we could think of it as right here, is what we measure, and that allows us, through the principle of alternate interior angles created by a transversal of two parallel lines. It's a fundamental geometric concept. Once we know this angle, we know is the same, because any line can be considered, if cut in two, its component angles always add up to 180, and then on the other side it makes a full circle. So this is 180 and this is the other 180. And with parallel lines, if we know that these lines are essentially at the same angle relative to the transversal, because these two lines are equidistant at all points, then if we know this angle, we also know that the interior angle of the other parallel line will be sliced at the same angle as this one was. So these angles are the same as, these acute angles are the same as these obtuse angles, in other words. That gives us this angle here. And so the principle, this right here, is the dangerous part of this example. And if it's confusing, it's A, because I'm probably a bad teacher, but B, because the concept of scale, I can do a better job on this piece of paper. I can use the total length, maybe even go diagonal and get as much out of the paper as possible. But still, this star in this system here, the Earth, Moon, and a distant star system, is so distant relative to the distance between the Earth and Moon that it's literally unfathomable. It's unimaginable how far away it is. Just by some of the little background research I've been doing, roughly, if this was even the nearest star to us, Proxima Centauri, and this was an accurate scale, on this scale of the Earth and Moon, and this isn't still, we'll talk about that in a little bit, this star would be, if in other words, the distance between the Earth and Moon was roughly, I don't know, we just so happen to have a ruler here, luckily. We'll just say 1.25 inches. This star, Proxima Centauri, would be, I want to say, miles away. On the order of miles away, at least. Just to give a rough idea. And that's the whole point, is that these rays are parallel for the concept of parallax to work. And they are. Practically speaking, they're parallel enough that we actually get an accurate distance. What distance we've, since replicated and verified many, many times since early Renaissance scientists were able to try to determine rough distances to the moon with telescopes and quadrants. And so that is essentially the concept there. And it's once we know this angle, we know to fair precision the distance between France and Athens. So we know this base side of the triangle. And then these two sides right here, it says X, and this side right here is Y. That would be the hypotenuse. And we know if we can make a right triangle, if we happen to measure the moon directly overhead, we can do a little math and we can account for the curvature of the Earth. So, on a closer scale, the curvature is going to prevent that baseline from actually being a straight line. We can account for the curvature of the Earth, which we've known since ancient Greece. And I think Aristarchus or Eratosthenes figured out the curvature of the Earth roughly to a great degree of accuracy, actually. We can figure out that we can orient it and situate the experiment so that the two cities and the moon will indeed, we can orient it so that the experiment allows that right triangle to be created. And honestly, even if not, it's not really the biggest hang up on this example, because there's also trigonometric identities and laws and principles like the law of cosines and sines, that, with which you can determine angles and side lengths of triangles, even if they aren't right triangles. I believe by splitting them into right triangles. So if you have a non-right triangle, I believe essentially you split this triangle into two right triangles. So any triangle, in other words, you can always split and then apply the standard sine, cosine, and tangent identities to it. And by knowing this angle right here, this is, if this is our angle, we know this side right here, this would be the opposite side from this angle. And, tangent might be a good trigonometric identity to apply here. So tangent is the opposite over the adjacent. And so the tangent of any particular angle is always a ratio. If we take the tangent of this angle, it's going to always give us the same exact ratio of the opposite side over the adjacent side right here. And this would be the adjacent. So if the distance to the moon from France is our x, or our adjacent side, we'll figure that out right here by essentially saying the adjacent side is going to equal, by doing some quick math manipulation of the equation here, you multiply both sides by adjacent, divide both sides by tangent, and then you have the opposite is going to equal the tangent of that angle right there. So by observing using very basic, hundreds of years old technology to measure things in angles in the sky, you get that angle, and by two parallel lines you get this angle, and we perform the tangent of that angle to get a number, which is going to be this. And so although we might not know these individual numbers, we know the ratio of them, because in any right triangle, the ratios of specific angles are always going to be the same. They're in tables, you can look them up. Tangent of 10 degrees is always going to be the same number, and that is just a ratio of the two numbers. So whether this side is 5 inches or 5 miles or 500,000 miles, in more accurately in the case of the moon, it's about twice as far as the moon actually is. It's just so fascinating that we can use these thousands of year old concepts, essentially, these concepts that were perhaps invented by the Egyptians, or continued from even older traditions by the Egyptians, and refined by the Greeks and passed on to the Arabs in the Islamic Middle Ages, and then passed on back to or through that route from Greece to Renaissance Europe in the late Middle Ages and early Renaissance ages. It's just fascinating that this very, very old mathematical knowledge can be practically put to use and determine the distance of our moon, how far away it is. And so let's see, if that is the side that we want to know is x, I guess we don't really care about this side. We just wanted the angle. These are our parallel rays. We wanted the angle here so that we can get this transverse, the alternate interior angle right here coming from the moon, basically the angle that the moon would make, or that these 2 points on Earth would make if they converged on the moon. We want that angle so that we can get our ratio. So x, and maybe we'll call this b for baseline. So it's just a general identity. That tangent of any angle is going to be the opposite over adjacent. And there's little mnemonics you can use to remember that. SOHCAHTOA is one. TOA being tangent is the opposite over adjacent. So tangent is the opposite of this angle over the adjacent. It's going to be b over a, opposite over adjacent, or sorry, b over x in our little use of our variables here. So b over x. And if we know what b is, so this now turns into x, or in other words, the distance from the France here, the Earth, to the moon, is going to equal our, what we decided was our opposite, b, our baseline, and we know that because we measured it. The distance in our little example here from Paris, France to Athens, Greece. So we know this, and we know that tangent. Tangent is always the same. Once we get this angle, that angle will give us a real value. So distance from Paris to Athens, a real value of tangent of whatever the angle is between that this star, the moon has created in its apparent position change. If we look at it relative to this star and how it's moved, whatever that angle that it's moved in the sky is what we plug in here, and that gives us the distance to the moon, which is, I think, roughly on average, because the moon does have an elliptical orbit, it's on average about 230 to 240,000 miles away. This, I've had these sitting outside the frame the whole time. Maybe you noticed the flicker of the candles, but I just wanted to give you a practical, small example of parallax with these in just a second. This example is great, it's fascinating that I just wanted to flesh that out real quick so that you understand the basic concept behind being able to use an angle that you figured out, and we'll get into how you figured that out, and the baseline, which you can imagine we figure it out. That's fairly simple mathematics to account for a curvature of the Earth, and we can draw a straight line there. So we can know these numbers. We can know that angle and that baseline. And as long as we know that we have a right triangle, or as long as we have a triangle whose side length down here we can at least know, we can apply, again, law of cosines or sines, different trigonometric identities. If it's not exactly a right triangle, we can break it up into manageable right triangles and figure it out with just a couple extra steps than we laid out here. We can figure out the distance to the moon, and that's fascinating to me. It's absolutely remarkable. It's a astounding statement about the ingenuity of the human mind and the intellect, and the fact that we've since been able to develop radars and lasers and bounce them off the moon to figure out that it takes 1.2 seconds for light to travel there, and then another 1.2 or whatever to travel back, and we can, based on the speed of light, measure how far that must have been based on how long it took the light to get there at that speed, is of course a whole nother ball of wax on the impressive achievements of humankind. But if we were to more accurately, let's not burn this, but if we were to more accurately make a sketch like I did here, and I want to do it because it'll make nice sounds and it'll be a little more fun. So if we elongate this, again, it's not going to be anywhere near scale, but if we make our Earth a little bit smaller and our moon and the star that we're referencing a little bit further away on this piece of paper, we might just be able to get a slightly better understanding of the concept of how, oh no, I lost my space there. How the enormous distances between bodies in the celestial bodies, objects in the universe like planets and stars, how these objects and their distances allow us to make these assumptions, like the rays coming from the stars and actually the sun, as I'm going to talk about in just a second, are allowed to be parallel because they're so far away. So I'm going to pretend our moon is right here. And then our star is going to be way out here. And this star, I'll give it a little bit of a dimension, is so far away. Now, even though they were dots in this depiction here, if I were, see, the issue was initially that if I were to make a quick replica of this without any of the lines in the way, and our star, way distant star, if I had our 2 points on Earth right here, and I make the hypothetical rays of light coming from this star, we can quickly see that the rays of light are clearly not parallel. They're coming from the star, and that completely nullifies our entire argument about finding that angle and having alternate interior angles equaling each other based on the transversal of two parallel lines. And that's always the part I got most hung up on. But it was by making this example right here and it's just a little bit, just a slightly more accurate depiction, of course, again, nowhere near the reality of it, that it makes the example that much more clear. And that's all I wanted to do. So if we now make our 2 points between Paris, France, and Athens, Greece, and then draw our line to the star, we can quickly see how this angle right here, I don't know, just placeholder, theta, phi. I got in trouble for the one video. What is one like that and one like that? Anyways, I just do it. I compromise. I make mine out of 45. But either way, we quickly see that this angle between the hypothetical rays coming from that star, or beams, I think is the more accurate term, gets much, much, much smaller. And if we were, again, even on this scale here, if this is, if we say roughly the Earth to Moon is 3/4 of an inch distant, then Proxima Centauri would still be a mile away, let's say. Now, or no, actually I know for a fact that's false. At least if the Earth, and you'll see how I know this in a little bit. If the Earth was this size, roughly the size of a marble, the nearest star would be, I think, at least 30, maybe 3,000 miles away, at least something like that, if not 30,000 miles away. So this here is about 12 inches away, or maybe 10, we'll say. So it's about 10 inches away, our hypothetical distant star. And this is, mind you, the 4 light year away, roughly, closest star to the Earth. Most stars are thousands, hundreds of thousands of times further away in just our galaxy alone than Proxima Centauri. So the more accurate distance, imagine this being even a mile away, but really it's more like 3,000 to 30,000 miles away. Imagine how small this angle would be. And that is the more accurate depiction of how these, in this example here, how these light rays could be parallel. Which then, of course, makes the trigonometry in our little example here more accurate. And I used to think that the sun was a lot like this, typical radiating beams of light out. Because the example I was saying was, even if the Earth was here in this example, you could still seem like there was an angle, because the sun being a spherical object, like all celestial bodies generally are, it's even at the closest, even at the, closest angles. So if the sun is like this, then more like we zoom in, and then we zoom in even more. Oh man, that was bad. Correct that. And then we zoom in even more. The misconception I had is that given that the sun is a sphere, as it emits photons, each photon is going to be emitted, I guess, in exactly a 90-degree angle or orthogonal to the surface of the sun from which it came from. And that's actually not true. The reality of the situation is that photons are emitted in essentially random directions, beams of light, no matter where they emanate from. So this same spot, over time, even though multiple photons emit from roughly that same spot, even if we zoom in to a microscopic level on 20 atoms across, directions of light, depending on, of course, the sun being a dynamic, essentially static, not static, a series of billions of nuclear explosions being held at bay and contained within roughly the same volume in space by its own gravity. We'll put it that way. So the directions of light of the photons are essentially emitted at random, based on whatever particular collision path they took during their 10,000 year journey from the nuclear explosions at the core to the bubbling surface of the corona from which they're emitted. And it's all random. So anyways, if you compile these up, you're just going to have, looking close up, a very incoherent direction among all the photons. It looks pretty chaotic down here. And then as we zoom out to, a quarter or half the sun, it's still going to be, very, very, very random. All directions of light. And then we continue that pattern. I'll do the ones orthogonal to the sun, but you also got to do ones almost tangential to the sun, and then every angle in between. So it's just chaotic. And the sun is emanating light from every part of it in every direction from it. But what we realize is that as we get further and further away from the sun, until even to us it's the size of our thumbnail held at arm's length, as it is from here on Earth, 92 million miles away, it becomes so far away. You know what? We'll make it more accurate. And of course, we know the sun is about 400 times as wide as the Earth. It becomes so far away that even though even the smallest section of sun is emitting photons at random, we're so far away that the light hitting us from the sun must necessarily have emanated from the sun towards our direction, and that is such a small portion of the sun. I think the biggest takeaway is that it's hard to understand, given that so much light, we can step outside on a sunny day and just feel the warmth of the photons interacting with our skin. We feel the warmth and the radiation of the heat and the energy it brings with it. But to give you an idea of how much actual energy output the sun is emitting, we are only receiving, if every direction of the sun is emitting this much, the same amount, we're only receiving the tiniest little fraction, almost imperceptibly small, of the sun's total energy output. And that is necessarily limiting the photons we receive to the photons that, no matter where they emanated from on the sun, they just happen to hit the Earth. So it's by the nature, I guess what I'm getting at, it's by the nature of the sheer distance away from the sun. Our sheer distance away from the sun that allows us to define the light rays that we receive, and that's not to even mention the stars and how many hundreds of thousands of times, if not millions and billions, billions of times further, how many billions and trillions of times further the stars are than the sun. That's not to even mention that. we're receiving such a small, infinitesimal fraction of the sun's light as we get further. I guess, yeah, to emphasize my example here. In each of these little diagrams, progressively zooming further and further out from the sun, these are the farthest possible distances that on the sun from which, between the photons that also happen to hit the Earth. And as we zoom further and further out, essentially we're pulling the Earth in these examples further and further away. Because if we're this zoomed into the sun, the Earth must be really close to be right here. So in each one successive little diagram here, the Earth is further and further away. And think about how much other radiation is emitting into space and never even being captured by our planet, let alone the other planets or other stars even, I mean, that's how we see galaxies, is by the starlight that's left over, that has made it out after it's been absorbed by all the gas and different stars and planets within that galaxy. And so all we're seeing is the light and there's plenty of it, because it's emitted in all directions very intensely all the time for billions and billions of years. And only that little sliver of the sun's light is actually reaching us. And that tiny little angle is, for all intents and purposes, parallel, non-existent, a trillionth of a degree, whatever you want to call it. We can probably measure it much more accurately and actually find it. I haven't been able to find it, though. I didn't look too hard, but it wasn't readily available information. Most all websites just agree that even for any scientific experiments, you essentially consider the sun's light rays as being parallel to each other. So that degree is so small. That gives you an idea of how far away we are relative to our sun, let alone how far we are away from this distance. Represents thousands of miles, even on these scales right here from stars. And that's what I want to continue to address with our small little scale of the planets, and put those in proportion, and discuss some of the other examples of here I told you I would show you parallax of scale in the universe and in the perspective that it lends us to really think about just how far, and consider how far and how small we are and how far apart we are from other planets and stars, let alone galaxies, like not to even mention galaxies. But right here, if we consider this, and if we, let's see, I'll try to hold it right here. And so if we look at one spot right there, and we move our position over, we can see if we hold the moon, the red little envelope opener, we hold that stationary, and we change our position with these candle stars in the background, we notice that if we consider they're far enough away where they won't change, they'll be in the same position, because relative to how far away they are, a small shift on Earth is inconsequential. And the moon is close enough to change its apparent position in the sky. So I just want to talk about the reality of the enormity of scales of the universe, and specifically the solar system, but we'll talk about some other concepts I've ran across too as well, dealing with numbers and size and time and distance. All that's to say, the units that you have to characterize space with are so large that you cannot visualize them on simple, confined, human-sized pieces of paper. And astronomically speaking, geologically speaking, even, our lives and our size are so finite and small that it's really worth doing a simple exercise to understand our scale and the true perspective that would show us our actual, places, our positions, our status, at least along those dimensions in the universe. And I don't think those are the primary dimensions, or at least not the primary dimensions. They're certainly significant, but the complexity of our brains and our neural circuitries, having hundreds of billions of interconnected neurons, are of course like I always mention. It's not common sense, but it's actually worth noting every time. I just mention it a lot. They're the most complex natural things that we know of in the universe. Our brains, let alone the interconnection of multiple brains of multiple humans communicating, that is, societies or even tribes. Those networks are the most complex things we know about. You can think of distance. You can think of you have space, which distance and size are a component, and then time, of course, the mysterious concept of time that just until Einstein was a static concept in the universe and just kept ticking at the same rate throughout the entire universe. And now we know that it's all relative and time is very distorted, and this tension with matter and mass and distance and light, time and space are in fact a unified thing, whatever that means. But I'm really just fascinated by how distorted this object is right here. And then you try to draw something a little more accurate, and you realize this diagram right here is still wildly distorted. Wildly. Like, not even close. Not at all. So, for the next 45 minutes, I guess, I want to try to counterbalance the very, very typical distortion of at least the solar system. We're just going to start with the solar system, because I don't think there's enough scientists, astronomers, that really do it justice, because, well, I think it's important to recognize and be exposed and learn properly accurate information, and recognize our true position, at least in space and time, in the universe. It's such an amazing thing to think about. The reason it gives us pause and strikes us with awe to really, really fathom our size, and not just the size, but almost more importantly, the distance, the massive distances between these astronomical objects. I mean, really, when you think about it, you can't even fathom the average human mind that doesn't actually regularly consider the true size and scale of, larger things on Earth and distances between cities, let alone Earth to Moon and the distances between the planets and even interstellar distances. The reason it strikes us with awe is because it's us, I guess, confronting an unknown. It's us peering into the abyss and seeing that there are things so enormous and so distant, things that we take for granted. You look up and our lives are determined, our circadian rhythms, our biology is set by the sun and the rotation of the earth. And every time the earth rotates such that the sun's rays beam upon us again, every morning, every day, our biology is reset, our circadian rhythms are reset, and we take for granted that this object is, this large. As we can see, I got a couple diagrams here. Let's see, it's the Earth-Moon distance there, solar system. Yeah, I guess that was the most accurate one there. Here we go. Yeah, just look at this. That thing that lights up our sky, that only looks about, the size of our thumbnail, held at arm's length, is this large. And this is us, right here. This little guy, right there. What is Earth? I don't know. The sun is, I just looked it up, it's 1.4 million kilometers. The Earth Wiki. What is the Earth? I think it's like 8,000 miles across. Radius 6. Yeah, so the Earth is not even 13,000 kilometers across diameter, and the sun is 1.4 million. 1.4 million. So that means the sun, if we do 1.4 divided by, so if we change 1.4 million into 1.4, then 13,000 would be changed into 0.013, and the sun is almost 110 times wider than Earth. It looks even bigger than that in this picture, but it's so massive that we really can't comprehend it. You think about really just the distance of a mile or two, and the brain starts to lose its ability to accurately actually think about and consider how far that would be to do a human action. Man is the measure of all things, as Aristotle said. We really do blissfully ignorantly go about our day. So many of us, I mean, not all of us, but I certainly do have and do a scary amount, just take so much for granted, including our small scale, our small size, in proportion to the quite literally unimaginable distances that lurk out in the unknown. The reaches, the cold, inhospitable, very, very inhospitable reaches of space. I want to just Well, first I want to, actually, when I was thinking about just, doing this video real quick, I forgot, I didn't consciously remember that I had seen this, but once I started, doing some real basic research to scale, I remembered I saw this video. It's a beautifully done video. Okay. I just want to show you. This guy does, so if you don't want to, if you're not trying to just zone out and watch my very, very glacial representation and presentation of this, watch this video. It's 7 minutes, and it's a beautiful representation of perspective, really. Just this part here that, let's see, where does he show? Yeah, he shows, like, this is normally, right here, is what we are generally shown, like, most all times. In fact, I feel like most people have not, unless you actively search for an accurate depiction of the Earth to Moon, which is literally what I had to do for here. You see the Earth, and you have to go all the way there to the Moon. Earth, Moon. It's actually unimaginable how far the Moon is. Again, it looks, we have no judge of distance. By looking at the Moon, we don't know its size, we don't know its distance. By looking at it without using very, very clever tricks and innovative ideas like parallax to be able to, and it's, the conjunction of parallax and trigonometry and doing a little bit of math and a lot of traveling to figure out the true distance. And look what he does here. I love this. It's such a genius representation. Look at that. That's actually the distance. It's obviously just a approximation, but that's much more accurate than what he had previously there. And so, yeah, I guess in my subconscious, my unconscious, I've been wanting to kind of just do a little video, just, talking about this for a while now. But, see, at the very end, what he does, using the Earth, that same Earth, he goes out to the desert and recognizes, and, he does the math and realizes that he needs to accurately portray and present the, not only sizes of the planets, but the distances between them. He needs, I think, 7 miles, he said, to get the full orbits. So when you think of a distance between the sun and a planet, that's half its orbit, So to get twice that, which would be the full ellipse, roughly a circle of the orbit, you would need twice that distance. So at that scale, where the Earth is roughly a marble, you need, I think, Neptune, the furthest planet out. Neptune is 2 miles from the sun, which is like a 4-mile orbit. Let's see. There's a visual, there's a great little visualization here. Is that it? Yeah, 1,000 feet from the sun to Mars. And just wanted to show you what the sun would look like if the Earth was a marble. I think he has it right here. Yeah, there's a better version of it. I don't know. I highly recommend watching this video. It's excellent. I don't want to get flagged for copyright usage. Is that it? clever. So anyways, at the very end, he shows the truck driving away from planting, and he goes out in the desert and successively plants the planets and lights them up for a display, and then does a time-lapse capture from a distant mountain where he drives with his actual truck and a light attached, neon light attached to the back of the truck. Let's see if we can get this. And it is, it's really wonderful to see the accurate perspective of just how far the planets are. So, let's see. Okay, right. Yeah, here we go. Okay. So he plants Neptune, the furthest of the 8 planets. And that's his car driving. And he zooms out. And you could see it's a 2-mile direct shot from Neptune to the sun, to his scaled model of the sun there. No, sorry, 3.5 miles. That's right, because he said he needed 7 miles, I think, total for that. And then, where was the sun? So yeah, if the Earth was the size, there we go, that's a good, accurate estimation there. So this, anyways, this is like a tent. That's a car. That's a whole vehicle. And remember, Sun to Mercury, Mercury to Venus, and Venus to Earth, roughly, very roughly speaking, they're about the same distances between them, same distances apart. And the Earth is the size of a marble, which means Venus is about the same size. It's 500, at that scale, it's 500 feet away from the sun. It's 500 feet away from the sun. So, roughly that's about here. That's about what we have. And the Earth would have to be, I would need 600 feet to draw an accurate diagram of the Earth to the sun right here. And I don't have a desk that long, or a house that long for that matter, or a yard that long. That's funny. Yeah, I need to go about 6 or 7 houses down and use one of their desks and draw a sun about the size of my desk, I guess. Which is, let's see, the field of vision. It's about 4 of these distances right here between my hands. So, where did I want to go from there? So many people jump to the idea that it's terrifying to think about these distances and, our small place in space, in the universe, how small and exposed we really are. But I think that actually, I wrote it down here to remind me. I think it really taps into our social instincts. We're fundamentally, we didn't evolve from herd animals like horses, but we certainly evolved in groups. And well, yeah, it was Jordan Peterson that brought this to my attention, that the environment that we evolved in can be more accurately thought of as a social environment than the actual literal physical environment of, whether it's forests and trees surrounded by, tree snakes and lions that might have, predators that might have eaten us, and and then later on, savannas and all that. Those environments are almost secondary to our perception, our evolved way of looking at the world. We actually evolved in a social environment. And what I'm getting at is that recognizing that the earth is such a small, priceless, small, fragile, paradisal blip, blue oasis in, the desert, the vast, cold, relentlessly hostile depths of space. That actually, to me, that activates, that incites, that inspires us to remember our most instinctual, perspectives of life, is that we're social animals and we are fundamentally part of a group that's become so large, so dispersed, that it's hard to remember that we are a part of it. And it's the human species. And we're the same way that we get that feeling of camaraderie and that very warm, fuzzy, safe feeling of being harbored from anxiety by grouping with someone ideologically against another ideology. We can, on a grander scale, remind ourselves by looking at our true place in the cosmos that we are on this oasis together. And we can group ourselves in with all of the human race. And then on an even broader scale, the entire animal kingdom, that we share the earth with. And it's really a beautiful thing. I think that's the biggest, I think that's the largest, I think that's the most profound perspective you can have, is to recognize that your life is larger than you, and you weren't created just by a single phenomenon of your parents procreating. You're just one link in a chain of hundreds and thousands and millions of generations of animals that eventually became humans, procreating successfully, mind you, and living long enough at least to procreate again and create a new generation. And you're the current link. You're the current, last, most recent link, unless you've had kids, and in which they're the current link and successor to this 4 billion year old biology that has evolved and adapted and successfully procreated in the what ultimately became social environment that apes, the monkeys, and eventually the greater apes, of which we're a part of, that we evolved in. So the social group is so burrowed and so deep and so unnoticeably saturated. It's so unnoticeably saturates. It so deeply, thoroughly saturates our perspective and perceptions of everything we do that we don't even notice it. It's part of the beauty of looking at psychology and astronomy and trying to find a link between the two. Is because I love understanding more about myself and trying to figure out what it is that makes me so not terrified, but in awe, in have a sense of reverence. It's like this weird fusion between a spiritual, religious experience and a raw, scientific, rational exposure to facts about the universe, that it blends and it kind of meets. They kind of overlap territory there when you look at the cosmos and our true perspective and our true place in it. I think fundamentally I wrote that the scale that I want to convey, that I will eventually get to in just a minute. I think that what it boils down to is that it gives us a perspective so grand and so large that the similarities of our circumstance outweigh our differences. And that's all. That's really what I wanted to get at. And very briefly, let's see. I wanted to show a couple pictures here. Let's see, downloads. Where are we at? Okay. Let's open all these. Will it work? Alright, beautiful. Okay. Some other things briefly that I wanted to point to when we're talking about scale and perception and things that we encounter that we probably have a skewed, distorted perspective about. Just much like this picture here and the distorted angle of the rays of light actually, coming from a star. And even here, that's, to us, that looks accurate. It's like, oh yeah, the Earth is so small there. That must be about the distance between the Earth and the Moon. No, it's, the Moon would more likely be about right here. Be about right there. And the Moon is the size of the United States, roughly. From New York, the East Coast to the West Coast, Maybe even further. It might even be out to about here, actually. So, I want to just draw the sun. We're going to find roughly a good size. I think I'm going to have to draw the Earth roughly about that big. Yeah, about that big there. So the Earth would be about that big. About the size of a peppercorn. And I think I'm going to go get one too, actually. So if the Earth was the size of a peppercorn, the sun would be, because if the Earth was this big, it would be unmanageable for our purposes here. And if it was the size of a peppercorn, it would be a lot more manageable. I think I would be able to maybe I'll be able to tape 2 pages together, and we can actually use this ruler and compass that I bought. I want to draw some circles and make some straight lines. Alright. I just really want to emphasize how often we go through life without recognizing the true scale of things, and the true and it works on, again, like with data, information. It works with time. It works with population size, and things like, I'm going to talk about, I only have 8 of these, but these were actually really interesting to me. This guy, John F. Miller, 86, says 78% of Americans don't even use Twitter. So that means 22% of Americans do. 10% of all tweeters create 80% of tweets. That's something called a Pareto principle, a Matthew principle, a Price's law, where a small, generally you can generalize it as the square root of the number of people in a system do half the work, roughly. And so 10% of tweeters create 80% of all tweets. So you got to remember that there's perhaps fruitlessly industrious. I don't know, is that an oxymoron? At least busy bunch of people, small subset of users, and I'm pretty sure this applies to all social media and all social institutions, the small, loud group who are feverishly working away at their little, pet projects are the ones who often make the most noise. Yeah, and I said, so that was 2% of Americans create almost 80% of tweets, less than 2. That's very, very, very generalizing here, but, roughly that's what that means, is that, and I got that because 22% of Americans use Twitter, if 78% don't, and then 10% of those people, and I know this is talking about globally here, so, maybe we can generalize that 78% and say roughly 80% of people in any given country don't use Twitter. And I know that would be very unscientific of me to just make generalizations like that, but we're just trying to talk about scale here, roughly. I just like the perspective. 2% of Americans create almost 80% of tweets. 2% of the maybe global population. 2%. It's amazing. And it's important because we don't act like that, We don't act like we're just hearing from 2 out of every 100 people. And then even further, narrowing the data points shows the actual users of Twitter. I'd say we could say about 70% of all users lie between that 15 and 25-year-old range. So that's most of the people you're hearing from. So of that 2% of Americans, 2% of the population, online, that are creating 80%, probably, 80% of those. Again, that law, it's weird how it applies across all scales. 80% of those are probably people between 15 and 25 years of age. Okay, this is a time perspective on time. It's probably one of the more common references to scale across time, but that's because it's so impactful that it's only 66 years between 1900, 1905, and 69? So 1904, 1969, something like that, that the Wright brothers flew the first extended, prolonged, was it more than a minute or 30 seconds or something like that, flight at Kitty Hawk, North Carolina. And Americans landed a man on the moon. A human being went from flying, mastering air, lighter than air flight, or not lighter than air, mastering the technology to create enough lift to sustain flight off the ground. I guess flight is off the ground. In 66 years, less than 70 years, they flew to the moon. And let me remind you, the distance to the moon. Where is it? Right here. This is the distance to the moon. It's not here, which is most often depicted. Yeah. Let's write that. So when you, oh, come on. My wireless keyboard doesn't want to work. There we go. Fell asleep on me. I guess that's pretty fitting. Oh, it's so delayed. That's annoying. That's really annoying. I need to just have a wired keyboard. solar system. So look at these images. And that's what this, the other guy from To Scale, he did at the beginning of his video, but I don't want to just record his whole video. But yeah, look at this. All of these images, every single one of them, they show, again, for practical reasons. I'm not judging, I'm just stating a fact that and these ones, the planets are even on top of each other. You aren't shown, even this one, it deceptively, looks like it's a little more accurate. And the Earth right next to the moon. And then this one, even, it's crazy how that's the standard version of what we think. Yeah, I mean, I'm sure everybody understands that they're not that close, but they probably have no idea how much further the planets are apart from each other than that. So, anyways, to finish, where are we here? Our little romp through Twitter, the scales represented on Twitter. This lady here, Chloe Baldery, she went camping for the first time this weekend with friends. Prior to this, I was ignorant of the Sisyphean task of collecting enough firewood to burn every day and every night through cold, rainy days in order to keep warm. Imagine our ancestors, how petty we sometimes are today. Yeah, it's, I don't know, it's very humbling to remember how much work it actually is to survive. And that applies to scale because the scale of society allows us to specialize and have engineers that aren't just good at building things. We have engineers, we have nuclear engineers, we have electrical, we have industrial. Within any given endeavor, infrastructure development, we have multiple engineers taking care of multiple components, or of particular components of that particular endeavor. It's just amazing the scale of society and what we're able to accomplish together. Here, from 1950 to 2020, last 70 years, another 70-year leap was infant mortality around the world. And this was deaths per 1,000 live births. And so we have black, dark red, light pink, and white. The black regions, or the really, really dark red, I don't know, it's low resolution, I can't really tell. You could see in so many parts of the world in 1950, higher than over one quarter of all births, over 250 out of every 1,000 live births died as an infant. And now, I don't see one nation that has that high, or even anything over 100, even anything over a tenth of births. So it's just amazing the progress. Uber Boyo, I've shouted him out a little bit. He's an interesting online presence creator. He says the 100-year war between England and France is what drove them to becoming organized nations. If you can rise to the challenge, the stress being placed on modern Westerners will shape us into an incredible new force of originality. Always think optimistic. Again, it's sort of the impetus for making this video, or at least me being interested, is, just part of my general perspective is the respect for perspectives. It's a meta perspective, I guess. The more I read and realize I don't know, the more I value multiple perspectives, and the more I revere and respect people who are able to take a more sophisticated approach to any given problem, specifically or especially social problems that are always multivariate, always more than just one single thing that you can easily point to and say that's bad, get rid of it, and everything will be perfect. Everything will be so much better. Everything is complex and has a lot of forces and tensions pulling at it, and you remove one, another tension might come in to fill the void, or the other side of that spectrum might overcompensate or overwhelm the system. You never know, and it's another reason why it's important to have a large perspective and respect and understand that what we have is not to be taken for granted, and we really should have gratitude for what we have. Something I struggle with all the time. Another perspective on time, much, much larger. You know what, before I do this, because this, it'll be a nice segue. Here, this guy, Christopher Conselis, I think he's an astronomer actually. We tend to forget that 1,000,000 is a huge number. If you go back 1,000,000 days from today, the year would be 718 BC. Everything that has happened since then, which is a lot, occurred less than 1,000,000 days ago. So everything that's happened since then is pretty much most of civilization has happened less than 1,000,000 days ago. And I remember the difference between 1,000,000 and 1,000,000,000 was, let's see if I can wake this up. Okay. Was putting it in terms of seconds. 1,000,000 seconds versus 1,000,000,000 seconds. Yeah, someone said that basically, 1,000,000,000 is 1,000 times. My keyboard stopped working, so I gave up on finding that. I think it was like 1,000,000 seconds versus 1,000,000,000 seconds. 1,000,000 seconds is like 20 years ago, 20, 30 years ago, and 1,000,000,000 seconds would be 1,000 times that. And when you really ask someone, like, oh, how long ago do you think 1,000,000 seconds would be? And then you ask them how long they think 1,000,000,000 seconds would be right after that, whatever their answer might be, whether it's 2 years in the past, and then 1,000,000,000 would be, maybe 10 years in the past. It's the perception of the closeness in relation of those two values that needs to be corrected, because we're surrounded by these large, again, time and space and complexity. It really, really pays to understand the significance between orders of magnitude. Especially with time and productivity, it really pays to recognize that incremental progress can radically change your life and your lifestyle and your, even your abilities, your skills, and your place in life in just a year. If you diligently practice that, and it really helps to motivate yourself to recognize the veracity, the reality of incremental gains. If you just do 10 push-ups a day, every day for a year, well, not only by the first month you'll be easily able to do 20, 30 push-ups, but by the end of the year you'll be doing 100 push-ups very, very easily. And it doesn't seem like that, but if you understand the I guess, the concept of exponential growth. And by understanding differences between orders of magnitude, that helps you understand and really, what's the word I'm looking for? Really comprehend, really wrap your head around, really take to heart and truly understand, I guess, is really in the truest sense of the word, to understand it, to be able to stand under it and grasp completely what that means, to recognize the difference between a million and a billion. If you can't do one push-up today, the visualization, the fantasy, the idea of you doing 100 push-ups in a row is so out of your realm of imagination, your understanding of what could be, that you're inhibited from even trying towards that goal. And that's my point, is recognizing the difference between a million and a billion, and that a million seconds is about 30 years ago, and a billion is 1,000 times that. It's not 100 years ago. A billion seconds would be, if given a million seconds being about 30 years ago, a billion seconds would be 30,000 years ago. 30,000 years ago. And that's the same thing. If you think about what a kilometer is, or even, let's say, 10 kilometers, that'll help my point. Yeah, 1,000 kilometers is, it's roughly, 600 miles? I think we can somewhat understand that, because that's about the distance most humans with a standard car could travel in about, I guess 6 hours, something like that, on the road, on the highway. You could travel 1,000 kilometers. And if we increase that 1,000 times, that would be 1,000,000 kilometers. And so if you think about the time it takes, 6 hours roughly, and we increase that 1,000 times, 6,000 hours. 6,000 divided by 40 hours, 150 work weeks. That would be the time it takes. No, let's multiply that times 150 million. That's the distance to the sun from the Earth. So it would be 22,500 work weeks if we drove. If we had a really slow spaceship that traveled at the rate that a standard, highway speed limit is, it would take almost 23,000 work weeks to get there, to the sun from the Earth. So, anyways, the last two I just wanted to show you here was in the same vein. The Tyrannosaurus Rex is actually closer to humans, 65 million years ago, than the Stegosaurus, 77 million years before the T-Rex, the Tyrannosaurus Rex. And I think that's like Cleopatra and Caesar and Jesus are all closer to us in history than they are to the builders of the pyramids. So to them, the pyramids were already older than we perceive, those figures of history, Jesus and Caesar. Even really anybody from written history to be from the modern era. And then lastly, maybe I should have put this in between the difference, distinction between Wright brothers to the moon and the T-Rex to Stegosaurus, but the time elapsed between the painting of these Ice Age horses, let's see, the Chauvet cave over 33,000 years ago, and the Niao, these are all French names, the Nio, I know the X is always silent, cave, about 15,000 years ago has passed. More time had passed between those two cave paintings than the more recent one to us, which is, yeah, that's bizarre to think about. Culture had been in stasis with minimal change, that minimal change, or maybe even backwards change overall between 30 and 15,000 years ago, and then relative to 15,000 years ago to the modern day. So my whole point is that it really is worth considering perspectives, not about just, distance and space and scale and of volumes and sizes of objects, but the scale of time and I guess the rate of change of objects too. That also falls into it. So I may or may not post this as part 1, but either way, maybe we'll make just a really long video out of this. But I do think it's an important topic and something that is not addressed nearly enough. So I hope it's given you guys some insight or sleep, one of the two. Either of the two is fine with me. Thanks for watching, guys. We'll see you next time. Bye. So now let's introduce some items. Let's get some ASMR sounds going on here. I have salt with sea salt in it, slightly larger kernels than the average table salt. We have peppercorn grinder here with whole peppercorns in here, and I think we're going to make Earth the size of a peppercorn to be able to draw the planets and the sun. The sun's kind of the limiting factor because if you take a peppercorn, the sun is 1,000 times, or 400 times larger. So if I stack 400 peppercorns up, I think the sun still might be kind of unwieldy, but at least we can sketch a portion of it, at least. I have some tape for the paper, taping the paper together, specifically to draw the sun. We might try to, obviously we're not going to be able to do the distances. I think the sun would have to be the size of almost invisible. It would have to be microscopic, or the maybe the sun, but the planets. I think Jupiter might have to be this size for the sun, for the distance. I don't even know. I think maybe if Jupiter was the size of a period, then the distances between maybe Earth, Mercury and Venus and Earth might be manageable within this frame, but we're not going to be able to do that. So we'll draw the planets to scale, and then we will talk. We'll talk about human scale objects and distances that the lengths, I guess, that the planets, interplanetary distances would be equivalent, analogous to, I guess. So I have a little box cutter that's somewhat round. A dog tag. The dog tag, Ernie's old dog tag from Miami there. I have some sticky post-it notes that we can, I think I might draw the planets and then cut them out so that we can move them around. At least the inner terrestrial rocky planets. And very briefly, I wanted to take the camera out of the holster real quick. My audio is gonna dissipate a little bit, but here's the entire desk. In case you guys were wondering, I got all my extra junk over here: the ruler and the compass and the calculator and our 1,000 Space Facts book, which I'm imminently going to be engaging, be initiating again. That series, we're gonna do part 2 out of probably at least 10 parts. It's gonna be 10 parts, so it might be like a 20-hour video. It might be the world's. I might shoot for the longest ASMR video record once I compile all those together. We have here's my AirPod case charging. Starting to get finicky. I got a little greenery over there I gotta have. This is my window that I have covered up. My little lights. I got the dogs hanging out down there. Brief look at the chaos behind me. that is waiting to be unboxed. Anyways, I took the phone off the holder to show you guys. Maybe 2 years ago now, I sanded down this old desk and put pictures under a layer of epoxy. I don't know. Maybe it's pretentious of me to think that that actually looks cool, but I was able to salvage a little bit of Jung. You know, maybe the dissipatory nature of psychology, of the mind, of the psyche. I don't know, I just like that a lot. And then this, I don't know, I guess this was one of the original pictures too, and I was able to salvage it, and I think it looks appropriate because it is representative of ancient thinking, and it's being eroded away at the edges if we don't properly preserve it and respect our intellectual history. I might edit all that out, but I just wanted to show you guys a common representation. Let's put the light over here, I guess. A common representation, I got that stuck down there, of scale is, different. This is 4 distinct orders of magnitude here. And it's just useful to recognize that we often do see pictures like this side by side. We see these two, and we think astronomy and space, and we kind of lump them in the same orders of magnitude, maybe, whereas they're many orders of magnitude different and distinct. So we have like let's just say 50-foot. You can see, I just love this picture. It's a painting of what I don't know if those are statues of, I don't know exactly where in Egypt that is, but it's the sand-covered statues of Egypt as they were found in the mid and late 1800s. And you can see how large the statues are compared to these individuals. If that's a 6-foot man, that statue might be 50 feet, maybe even larger. If we say 50 feet, and we remember an order of magnitude is 10x larger or smaller. A million, the difference between a million and a billion is 3 orders of magnitude, or 1,000, 10, 100, 1,000. Then this 50 times 1,000 would be 50,000 feet. And that's about, roughly 10,000 miles. No, sorry. 50 miles. So, because a mile's roughly 5,000 feet, 5,280 feet. So, miles, I guess. this progression of distance is kind of representative. There's a jump. This picture is probably roughly, 1,000 miles, maybe 500 miles. So it's about 50, maybe this picture of the Nile from space is about 50,000 times the scale of this. And then this picture of the Earthrise, which I really, really love. I got a little poster it's hiding up there. I'm gonna have to make that more prominent, but that's 200,000 miles. It's about 200 times, maybe 200,000 miles. What would that be if that's 500 miles? That'd be 400 times the distance there. So it's just interesting when you actually understand the perspectives, which I certainly don't, but I'm on the road to getting a better understanding of it. When I look at things, I want to try to comprehend more easily and readily true distances when I look at pictures like this. And then this is the Andromeda galaxy, which is 2 million light years away, which is many orders of magnitude larger than the Earth-Moon distance. I just thought it was an interesting juxtaposition. So I think the best way for me to learn a lot of times is to comparative learning. I don't know, I just think comparing things is one of the best ways to learn, because everything is relative to other things, including words. We define words as they become more abstract and less literal, like a rock, wood, tree, natural, nouns. We define words using other words in their relationship to each other. And that's what I want to do with this, is because we can't directly access the planets other than by looking through a telescope or looking at them as points of light. Maybe Venus and Mars look a little brighter than other planets. And with a telescope, we can start making out Jupiter's, moons. It's like looking at things with one eye. It's really hard to have a sense of depth. Okay, so here's our bucket. We have our scissors. We have some pencils. Probably use a pen or a pencil. We'll cut the planets out if we want to. And again, we have our ruler here, stainless steel ruler, to make some straight lines. Our compass to make some symmetrical, some accurate circles, I suppose. Is there a mustache sticker hiding in there? I think there is. That's really interesting. Scan to claim your free gift. Mr. Pen. Then we got a calculator and a tape measure, like I said. Okay. The distinction between a million and a billion I might have found it. I don't think I found it on this website, but betterexplained.com. This article is called How to Develop a Sense of Scale. And this might be the most, again, we understand things much better when it's in terms of human scales and human objects, human ideas. Money is a pretty important human idea. In fact, that's a whole nother thing I want to get into with Bitcoin. And money is a store, not of value, but a store of energy, because it represents work. It represents energy and human labor and work. So anyways, again, it's all about perspective, you know. Bill Gates here has $56 billion. Okay, so this article was written a while ago. He has like more like 100 billion. Oh, he just got divorced, so I think he might be back to 50. Bill Gates earns, what that means is that he earned over $3,000 per minute, $50 a second, $50 every second since Microsoft was created. Spending 5 seconds to pick up $100 off the floor is literally not a good use of his time. Think about that. Not a penny, not a quarter, not a dollar, 5, 10, 20, a $50 bill. If he sees a $100 bill on the floor, if it takes him 3 seconds, more than 2 seconds to bend down and pick it up, unless he's really looking for the exercise, he is not saving money by picking that $100 bill up. That's phenomenal. I got Ernie and Gracie in the background, by the way, in case you're wondering what those sounds are. Yeah, this they point out that Apple, and this of course states the article, and this is an iPod Touch. Maybe it's like 2000. This might have even been before the iPhone came out. So we see a brilliant marketing strategy. Apple knows this. Man is the measure of all things. They measure the iPod relative to 2 very, very common everyday items: a pencil and a manila envelope. Or they measure the MacBook Air in terms of it being able to fit inside a manila envelope, which is a very, very memorable comparison. Okay, and it says we have you go to the hairdresser, and if you're not familiar with blade sizes, they maybe talk in terms of finger lengths, you know, and you immediately understand because it's your body, things that we're familiar with. Okay, this was where someone must have tweeted it, because I know I didn't get it directly from this website, but this is the comparison between 1,000,000 seconds and 1,000,000,000 seconds that I was looking for. 1,000,000 seconds is 12 days, or a short, vacation. So I was off by an order of magnitude there. No, by three orders of magnitude, 1,000. I was thinking of 1,000,000,000,000 seconds being 30,000 years ago. So 1,000,000 seconds. 1,000,000 seconds ago was 2 weeks ago, roughly. The middle of last week. 1,000,000,000 seconds ago was 30 years ago. I've been alive for roughly 1,000,000,000 seconds. That's crazy to think about. My entire life is just 1,000,000,000 seconds. I'm almost 32. I actually stopped counting after 30, not gonna lie. I forget whether it's 30, whether I'm turning 32 or 33 this year. Anyways, 1,000,000,000,000 seconds. 1,000,000 millions 12 days, billions 30 years, a trillion is 30,000 years, longer than the entire duration. It's 3 times, maybe even 6 times, depending on whether it's 5,000 or 10,000 years ago that you want to establish human civilization as. But written civilization roughly is 6 times younger than a trillion seconds ago, a sixth. So it's only about 15 billion seconds, I guess. No, sorry, 150 billion seconds, roughly. Wow. And then distance, the similar effect. If we use a millimeter, 1,000,000 millimeters is a kilometer down the street. About roughly about half a mile. 1,000,000,000 millimeters is 1,000 kilometers, roughly 600 miles, and a trillion. So we go from down the street at 1,600,000 miles, along a city that's a long day's car ride on the highway away at 1 billion, and then 1 trillion millimeters is going around the world 25 times, almost as wide as the sun. Then it goes into other things, numbers. The number of people on Earth, number of internet pages, both which have risen pretty dramatically since this article was written. So I wanted to just point that out because the million billion distinction is pretty huge. Okay, so, and then this, maybe I'll just add this at the beginning when I talked about it, but this is actually someone wrote on Hypatia Alexandria, although she calls herself Demeter Alexandria here, unless maybe her friend was Demeter Alexandria. There are a couple of Alexandrias. She wrote a Medium article, which is actually worth a look if you actually want to understand just how to practically understand the measure and derive using high school, advanced high school, I guess we could say, geometry, using like the law of sines, and because we're not exactly using a right triangle, but you can break other triangles up and either into right triangles, or you can use other characteristics of trigonometric identities. From Minneapolis, Minnesota, in Santa Fe, New Mexico. She had her friend somewhere, I think in New Mexico. She was in Minneapolis, and she took a picture of the moon, and her friend took a picture of the moon, and what they did was leave the camera lens open long enough to expose, for the exposure to I'm pointing to the screen with my finger, but to get the star Theta Lyrae. It's a bright star, and we could see the measurement, the difference. Of course, they were able to use modern technology to communicate and time their pictures to be taken within, probably at the same time, within a couple seconds of each other. And so what that does is give you essentially, once you understand the size of the Earth, the curvature of the Earth, the distance between the two locations that the camera was taken at, you could see how the moon appears to have shifted with respect to that, what we consider is so far away that it's static, it's stationary. It's the independent variable in the measurement there, and the moon is dependent on where you're measuring. It's a lot closer. It's the thing that changes. And so she took a superposition. She superimposed the pictures on top of one another and did the math to figure out how many pixels are equal to a certain degree, using some software or something like that. She figured out the line between the two locations, but she got an accurate measurement to the moon by getting the angles and knowing the distance. So she knows one side of that triangle. She knows the angles right here and here. She was able to figure out the third angle. And once you know enough characteristics of any particular triangle, you can always figure out the remaining sides and angle lengths, side lengths and angles. Yeah, pretty cool. So I just like the idea that it is actually possible for the layman to understand where we understand, how we know the distance to the moon. I feel like it's so glossed over how we know, the universe is as big and old and distant and, energetic stars. All these characteristics about space that we all love to learn about, because it's a way for us to confront the unknown. It's a minor adventure on a small scale, but so often they gloss over how we know this. They say, we know this, this, and this. You should be amazed. Wow. It's I think it's amazing that 400 years ago, these really intelligent, really diligent observers of the cosmos. And of course, these people were always princes and well-to-do people. If they weren't geniuses that worked their way up, they always had plenty of resources. But I just want to show you here the ancients, at least in the West, in Greece, they already understood the concept of parallax because they used triangulation, a version of parallax, to calculate distances to ships in very practical. Again, I've talked about this before. A lot of inventions come out of struggle. Well, no, I guess it goes to what I referred when I was referring to Uber Boyle in his tweet, was talking about how the tension of war and warring ideas on a more abstract level creates the impulse to make new innovations and propel us forward by necessity at a quicker rate than we otherwise might. At least that's been our history, and a version of utopia might be in the future for us to be able to teach and educate and raise our young children in such a way that they understand the finitude of life without having to endure the exposure to war and horrific trauma like that, by teaching them in a very hands-on way about all the mysteries of the universe that we know, how we know them, and then once they understand that, we can expose them to the mysteries of the universe that we've yet to figure out. And that call to adventure, that unified solidarity among humans to have a single, or at least a small subset, a small group of mysteries to solve, and things characteristics about our existence. We say the universe, but really it means our existence. We're born and we die, and in between them, we want to figure out as much as we can. We want to peel back the layers of nature as deep down and as microscopic and as far away and as macroscopic as we can to really understand what the nature of it all is. The meaning, the purpose, the origin of existence, perhaps the final destiny of our existence in the universe. Here we have a sextant, the word I was searching for earlier. There's other astronomical instruments to measure angles, but a sextant is called that because it's a sixth of a circle. A quadrant would be a quarter of a circle. And this was one from 1449, at the end of towards the end of the Islamic Golden Age, scientific Golden Age, where the Islamic Byzantine Empire of Eastern Europe and Western Asia, the Middle East, was a absolute melting pot, a cultural sponge absorbing ancient information from the west and to east. And this prince here, for more than 1,000 years, Ptolemy's Almagest was the world's standard authority on star positions. It's translated into Arabic. In Ptolemy's work, although he was wrong about thinking that it was a geocentric universe, the Earth being the stationary object around which stars and everything else, the sun, planets, rapidly rotated, he was right about a lot of other things, and he made a lot of useful, detailed observations that helped us ratchet up our knowledge about the universe as it was transmitted across time. And so Ulugh Beg was the grandson of a Mongol conqueror, Timur. Lived in present-day Uzbekistan in 1409, and he turned the city into a respected place of learning. So anyways, this was his remaining trenches, you can see here, gouged into a hillside for observations. Here, this is a diagram I just wanted to show you. This right here is why it's so hard for me when I'm not diligent enough to actually really thoroughly read descriptions and I'm relying on diagrams. This is so distorted that it really makes it hard to understand the principle behind concepts. And parallax here is saying that this star looks, these large stars here, so it's really, much closer than these background stars, but to us, just looking at the sky, they're all just on one apparent single distance away, one big wall, really, really far away. And in June, on one side of the sun in our orbit, this star would appear like this, and then as we travel on the other side of the orbit, it would appear to move with respect to the more distant tiny stars in this diagram. But in reality, where did I put that? Here we go. In reality, maybe I can do this, actually. If we look at this as a triangle, this rubber band right here. Here, let me give you a better view. Okay, so if I can somehow keep these scissor legs in position, and this between these legs is one angle, one side of the triangle, and I sit and I pull this, the lines of these two sides, as they get longer and longer, this angle here is going to get smaller and smaller and smaller. So this angle is much smaller than this angle right here. And just imagine that this is drawn out. This point right here, represented by the flathead, the little screwdriver, is drawn out 1,000 times further than these lines would appear to be practically parallel. And that's how parallax works. That's one foundational concept on which parallax is applied. Okay. See, I have my little list right here. Astronomy book, rubber band example, and then now, finally, the grand finale that we've all been waiting on. Let's go back to our monitor, and so we have this website, exploratorium.edu. We're going to find out, we're going to calculate the radius, and we're going to try to get the sun's radius at, see, body diameter. We're going to make that 12 inches. And then the orbit radius, if the sun was a foot across, Mercury would be 40 feet away, Venus 77, Earth 107, Mars 163. Jupiter would be 559 feet, Saturn would be 1,000, Uranus would be double that, Neptune would be over triple that, and Pluto would be quadruple that. And this is, roughly these are the average orbits. Okay, so the body, the sun is 12 inches, a foot in diameter. Mercury would be 0.04 inches, 1 millimeter. Okay. Earth would be 0.1 inches, 2.7 millimeters. Alright. Millimeters, centimeter. So, Mercury would be about the size of a grain of salt here. And then we get the peppercorn out, but it's roughly a little bit bigger than that right there. That would be about what Earth is. Okay, so let's do that. Let's use that. And then Jupiter is going to be 1.2 inches, 30 millimeters. Saturn's going to be a little smaller at 1 inch, 25 millimeters. And then Uranus and Neptune are going to be 0.4 and 0.39 inches, respectively. Pluto would be 0.02 inches. Okay, so let's go ahead and draw this. Let's see if we can get this into a. Let's see here. I think and this is a Bitcoin, by the way, guys. No, I'm just kidding, it's a bog. Slammer Whammer in 1994. It's an 8-ball special. I honestly don't even know where I got this. It's one of those things that's just floating around your drawer for years and years, and apparently for me it's been about 30 years almost. Okay, we're gonna I think I'm gonna actually dispense with those objects. We're gonna make a bunch of little circles on our sticky notes, cut them out, and see. Let's see. Jupiter's gonna be an inch, yeah. So, and then we're gonna draw the sun. And I really want to. I mean, I guess it's easier to just talk about it, but it's just amazing that, you know, if the sun was 12 inches across in diameter, Mercury would be 40 times this away. 40 times this. And it would be the size of one of these grains of rice right here. Salt, not rice. See if I can get one out without breaking it. I think Mercury would probably even be smaller than that, but yeah, roughly that's what Mercury would be. Right there. So the sun would be this large. That across. Mercury is that small. And you can't really do the masses, the actual amount of matter, and even the volume that that sphere would take up by looking at simply the diameter. So set Mercury aside for a second. There we go. Put Mercury right there. The bottom of that triptych. Right there. Triptych. Okay. Alright, so if we got Mercury right there, Mercury and, you know, in fact, all the terrestrial planets are so small that I'm just gonna we'll just we'll draw and cut out the gas giants, in fact. Okay, let's open this up. Okay, making a little bit of a mess here. Oh yeah. Right. Got loose whole peppercorns in here. Got whole peppercorns in here. Okay. There's a couple peppercorns. A couple planets. Okay. So we got Mercury, Venus, Earth. I wonder if I could find a small enough peppercorn to represent slightly smaller. Oh, there we go. Look at that. Nice. That's a little guy right there. that actually works out pretty nice. Look at that. Look at that, guys. Would you look at it? Okay. save that for dinner later. If I did a scale model of the actual solar system here with a working orbit, that would give a whole new meaning to the word seasons, wouldn't it? I'm a dad and I was obligated to make that joke. Okay, alright, let's close this up. So Molly's none the wiser when she cooks later. Okay, so we got our inner rocky planets, terrestrial planets, and we're gonna have our gas giants, which I guess ideally I'd have little balloons because they'd be filled with gas, but I don't have balloons, so we're gonna use paper, roughly two-dimensional paper. Okay, alright, so I think, and just because I haven't really addressed the rest of this little back of the envelope calculations, as I was trying to say, just wanted to point out real quick, just wanted to address this and this. If the Earth-Moon distance was 1 inch, the distant star would be almost 39 miles away. So this, if we consider a star that's 100 light years away, if the Earth and Moon are, I should have got another grain of salt out for the Moon, because it's roughly the same size as Mercury. But yeah, the Earth-Moon distance, if that was 1 inch, and if it was 1 inch, then that would represent 220,000 miles. The Earth is roughly a 20th. So a 20th of an inch would be way, way smaller than that. For the Earth-Moon distance to only be 1 inch apart, Earth, if that was the Moon, that was Earth, Earth would have to be invisible. 20th of an inch. It would have to be maybe a millimeter, actually. So I guess half the size of that right there. I think I might be able to just knock this in two and make Mercury and the Moon out of it, because that would be more accurate. There we go. Okay. There we go. Alright. Here we have the first planet, Mercury. Then we have Venus. Slightly smaller, but roughly the same size as the Earth. And then here's the Moon. Okay. And then we're going to figure out how far apart these have to be. I already told you, but we're gonna address the Earth-Moon distance. I want to make the Sun and the planets. So at least we'll do the Sun, and then maybe we'll talk about the Earth-Moon distance, and we'll talk about the relation. The relation in distance, in size to the Sun, and then we'll go on to the gas giants. All right, so the Sun. Finally, we can open up our compass. that to the side. And now let's get to drawing our sun. Here's our compass. I actually do need the little opener after all. Let's see. Okay. It's really hard plastic, so bear with me if I make any sounds that I forget to edit out. Okay, we got, I think this is an extender. Here's the compass. This device here, threads, you rotate them and they incrementally increase the diameter, the distance between the 2 points. Oh, we got screws falling out here. I don't know what this is for. I guess it holds this in place. Okay, shoot. What is going on? What's going on? I don't know what those do. Why is that there? Okay. Little bits of lead. Got little accessories. I guess those are replacements. Okay. The extension. It's lead goes in there, and this extends to make much larger circles. Okay. Random mustache. That would be about 300 million miles long. And then useless paperwork. Okay. Wow, that's quite the guarantee. If you're for any reason unhappy with your order, no matter how long it's been, I'm gonna save this till about 2040. We'll see about this guarantee, Mr. Penn. We'll see about that. Alright, so, no, I'm just definitely kidding. I would never do that. Okay, so, back to the website here. And I just wanted to remind you guys that, so our sun, so if this is, that 1 pixel is the moon, our sun, let's extend this a little bit. Sun would be this big. And our sun, it's going to be about twice the size of that. So, and then here, let's go over a little bit. Oh, I can do miles. That's pretty cool. Blue whales, great whales of look at that. That's really cool. Earths, man. Look at that. That's pretty cool. 80 Earths, 100 Earths away. So miles. But yeah, 1,000,000 miles. So I could do this for a while. Mercury's going to be 30 million. Yeah, about 30 million miles away. And there we go. Zip, 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 zip. 35 million. Venus. Another 30 million. And then Earth. Another 30 million. Oh, there we go, that one. So you see the distances, and if I zoom in, I want to make Earth, let's make Earth the size that we're working on here. Alright, so it's still smaller, but let's get our ruler out. So we might need to make some straight lines. And I got these made out of steel. I just wanted some metal rulers that wouldn't bend. Wouldn't bend very easily. Alright, so let's see. Let's break out the big boy. Alright. Man, look at this. Yeah. Inch to millimeter conversions. 1 inch is 25.4 millimeters. Wow. So the closest distance to 1 millimeter would be 1.19 millimeters at 3/64ths of an inch. I think that's what I see. Yeah. Okay. We're gonna be drawing some serious lines with this. Okay, so here's our standard by which we're going to measure things. Got millimeters up here, inches down here, and let's get a piece of paper. All right. Okay, so let's see, given that the sun, where are we at here? Here we go. Alright, so the sun is 12. Let's see. Alright, here's what we're going to do, because these peppercorns and the grains of salt here are what we've established. So they're not going to change. So we can alter the size of the sun based on the size of these. I want to measure these. Let's see. Let's measure the Earth. Let's pretend that's the actual real measurement here. And actually, look, this is where this can be pretty useful here. Assuming we can get close enough. I don't know, can we? Can we? Alright. Look at that. Okay, fantastic. So I got it close enough to be able to pick it up. And then, awesome. So I know that's the exact, as accurate as we're going to get using the compass. And then now I look at this. You know what, we're going to use millimeters. Yeah. So, let's see. I'd say it's 5.5. Alright, so it's 5.5 millimeters. And now we're going to enter that. Yeah, we're going to enter that. Okay, so that's 5.5 millimeters is what our Earth is. Let's enter that. 5.5. Enter. Nope. Calculate. You filled English and metric boxes. You filled in. Close. Okay, hold on. Okay. Alright, so all we have to do here is man, I messed that up. Is mess around maybe with the sun's diameter until we get 5.5 close, 5.5 millimeters. Let's let's make it 14 inches. Oh, wrong one. There we go. 14 inches. Calculate. All right. So let's do 20. Calculate. Oh, forgot to clear. Computers are very good rule followers. Very good rule followers. That's why we got to make our rules. 25. Easy to follow when you're programming, I guess. Okay. All right. So that's awesome. Actually, that's pretty cool. All right. Let's make it 24. I think 24 might be right. 24. Calculate. Nice. All right. Great. And you might hear Molly's mom, June's grandma, out there watching baby June right now, so there might be some baby sounds in the background shortly. Okay. Alright, let's set these aside, even further aside. There we go. Got those hanging out there. And now we have an order. Oh man, what was it? This one? So in order for Earth to be 5.5 millimeters, that would mean the sun is 2 feet, exactly 609.5 millimeters, or 2 feet, 24 inches. Two of these right here won't even fit in camera. That's awesome. But that is the diameter, so that's actually really perfect, because that means that this right here, from here to here, is going to be the radius of the sun. I just think it's so important. Like, I'm really just doing this really selfishly, because I really have always wanted to see. I want to, visualize and draw out the true scale of the sun myself. Oh, look at that. So you can quickly. That's such a neat little feature. You can press that. Ernie, lay down, buddy. Alright, you can press that feature and it loosens it up. So you bypass having to wheel if you really want to make quick adjustments. That's Mr. Pen, I gotta give it to you. I promise I'm not sponsored, but I would not mind being sponsored by Mr. Pen. I'm impressed. Okay. Alright. Let's see. Okay, so I gotta attach these real quick. Like this. I'm not really sure. There we go. Okay. Alright. So we got those locked in, because we don't want those moving. Even though these aren't going to be the most accurate measurements ever. Alright, and then this one goes up here. Alright. This one goes through here, I believe. Like that. Alright, I think we're on track here. Maybe like that. Then, convex side out. Maybe. Maybe it doesn't matter. I don't know. Alright, so we can't do 12, because this works like you put it in the center and you scribe around the center. So this distance would be the radius, and it doesn't look like we can reach. We only have about a 5.5 diameter radius, and that's why I bought this one, because excuse me, I wanted to try to make something similar to a 12-inch radius sun. Okay, how do I do this? Can I do this without reading the instructions is the question. That's the question. No, I can't. Well, hold on, Richie. At least I have to try. Let's see. You guys are probably laughing at me now. I guess you attach this. How does this attach? Alright. Maybe I'll take out the lead. Get the lead out. Like a classic rock station. Man, that thing is in there. That is really in there. Like swimwear. Where's my tools? My tools. Here we go. Let's try to not break this. There we go. Alright. I'm gonna get the right tool for the job. Okay, I know it looks like this. Essentially, let's put the lead in here. Let's put the lead. Let's see, make sure. How does that work? What the heck? Okay. Let's check this out. See, I know this is ASMR, but it's bordering on being really boring also. Alright, what is this? What is going on? Okay, we got a couple more pegs. I don't think I needed any of that. Look at that. 24 inches in diameter. Perfect. This is a little bit embarrassing. I'm not sure how much of this I'm going to leave in. Okay, this slides along here. I know the lead goes in here. I just don't get... Oh, maybe this part comes off? Is that what happens? And then it goes like this. Okay. Man, I would have not been able to figure out parallax if I was in ancient Greece. Oh, look at that, and that little fork right there. It's another reason why I just love learning. It's because you start appreciating things. You start appreciating good ideas so much better. A little fork. It wraps around the inside of this wheel, this little bar, the screw right there. And that screw nut system compresses the plastic right there. Man, that's a really cool design. I like that a lot. Okay, press it there, tighten it down. And then, so looks like I didn't have to take that out after all. Tighten this back down. And then let's pop this in here right here. Didn't have to take this fully out either. That's okay. That's okay. Alright. So we got the screw here, and we'll leave it slightly loose. There's Graham out there telling June how good of a girl she is. Oh man, I love it. Okay, and then, let's see, yeah, like that. Alright, and then we can just adjust this accordingly, but the max is a 12 inch radius. I just heard June squeak. Oh man, she's 4 months old right now. It's gonna date this video. I hope she gets to watch this. I really wonder sometimes how long YouTube is gonna be around. I wonder if she'll be watching this. Well, she'll probably never watch this, but no kid is generally that interested in what their parents do. But I do wonder if like this, I'll have it stored on a local drive, but I do wonder if it's going to be on the internet 20 years from now. Alright, it's really, okay, I guess that's as far in there as I'm going to get that. Fantastic. Okay, let's measure a 12-inch diameter and get to drawing this sun that we've been waiting 3 hours for. Let's max this thing out. Wow, look at that. Okay. To fit on this single sheet of paper, we'll tape 2 pieces together, but for now, let's just get a rough estimation. Ooh, that's almost there. Let's go all the way out. And there we go. Awesome. Alright, you guys see that? Can you guys see that? So I have from there to there. That's half the sun. It's gonna be a big old circle. It's gonna be a real big circle. Okay. Let's flip it over to a fresh side. You know what I'm gonna need? That is awesome. It's gonna be so massive. That's so cool. Alright. Is that gonna be? Let's do we'll start with these 2 pieces. Oop. Oop. All right. Let's do this. Well, at least that's good enough. Let's do this. Okay, alright. Yeah, let's go ahead and tape the corners. Alright, guys. So, you know what I actually might do right now? Utilize this fisheye lens. I'm gonna take a risk. Hope it doesn't screw up the whole video file. Cool. Alright, I got the whole paper in. Awesome. Okay, so here we have our planets. I forget which one was Earth. Earth here. Mars is about 2/3 the size of Earth. Venus is about same size as Earth. It's a little bit smaller here, but if that's Earth, it's Mercury. This is the moon. Alright, you want real quick? If we know Earth is 5.5 millimeters, we can, let's just do how many Earths fit between the Earth and Moon. Right there. Very common questions. 30 Earths. Okay. So 5.5 times 30. 15 plus 150, 165, I guess. Okay, so if this, let's write this out. So I'm gonna do Mercury right there, Venus right there, and then Mars is gonna be twice the distance there. So Mercury, let's go back to that's Mercury, and this distance is actually about 40 feet. Venus, Earth, and let's find out. 165 millimeters. Oh my god, that's so that's a centimeter is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 1, 2, 3, 4, 5, 6, 5. Okay. Does that fit right there? Wow, look at that. Okay. So 165 is right there. Is that even? Okay. It's in frame. Just making sure. Alright. So 165 is right there. The moon right there. And let's use this extremely straight ruler and draw a line right there. Knocked Mars out of orbit. Excuse me, Mars. Man, look at that. Look at that. Okay. Alright, guys. This. Oh, I thought I lost Moon for a second. The moon. Okay. Just gonna draw a circle around it so we can see where the moon is. The moon, I was hesitant to do that because it makes it look much larger than it is. Yeah, let's not do that. I want to try to convey the actual size of the moon relative to the distance away from Earth. So. Alright, there's our moon. Right there. Grandma narrating her day to June. I love it. Alright. Okay, so if that's the Earth, the Venus, Mercury, the Earth, this is about as accurate as we can make it. That right there, that little guy is the moon, about the size of the United States. Earth is about 8,000 miles across. And if that's 8,000 miles, that's 30 Earths, about 240,000 miles. On average, it's an elliptical orbit, but just imagine that before we draw the sun. Just imagine that being like right there. You know, the moon goes here. Its orbit is about that big, and that's Earth. So every time you look up, I want us to remember, if anything, the Earth-Moon scale. I want us to remember to take away the true distance. And the moon looks big. It's just amazing how large, how clear, too, that it really is. When you look at it at night, sometimes I genuinely wonder, like, I've never actually done, again, this exercise. So this is just a personal interest of mine that I wanted to explore and elaborate and understand for myself. Alright, so okay. Let's do one more little piece of paper. Or you know what, we don't have to go through all that. We can just do a sticky note. Let's see. Right there. About right there. Okay. That's gonna really stick that in there. Okay, let's go back out to fisheye lens here. And here we go. We're gonna draw a section of the sun. Let me open it over the curve here. Oh my god. Oh my god. Look at that. And this. So that's Mercury, Venus, Earth, and my sweaty palm just picked up Mars. And then Mars out here. And then this. I don't know. Write it. Let's do it down here. Is the sun. And that's the sun. So now if Earth is 62 millimeters, okay. So if Earth is 5.5, let's, you know what, let me, it looks like it changed a little bit, of course, but whatever, that's fine. Just want to note that that's the center of the sun, where all the nuclear fusion is taking place. Just picked up Mercury, I think, too. Sorry, Mercury. Alright, so the hottest star is 18 feet. Distances and speeds. Trying to understand whether it's the radius or diameter. Yeah, the sun's given in the diameter, so we're going to assume that it's the diameter. 18 feet. That's another diameter. That's another 9 times the sun. And the coolest star is only about 3.8 inches. So that tiny compared to the sun. And then a red giant Betelgeuse, not even the largest red giant. So there's stars even larger out there than Betelgeuse. But Betelgeuse, which is in it's the top left shoulder of Orion, I believe, is 750 feet on our scale right here. 750 feet. It's 375 times what our sun is right here. Sorry if you can hear that, that's June. She's having a meltdown out there. I guess she's giving the grandmas a run. The second grandma just showed up, so the grandmas a run for their money right now. It's the only way I can get this video done, so bear with me if there's a lot of editing. And then a white dwarf. Very, very small. Generally the core or the remnant after supernova or red giant sheds its outer atmosphere, I believe, generally. And a neutron star might be the remnant, a stellar remnant of a supernova explosion. White dwarf is only 6 millimeters, so barely larger than Earth. So the white dwarf is a quarter of an inch. And the sun, technically, is classified as a dwarf, so it gives you an idea of the scale, the magnitude on which dwarfs exist versus the red giants, for instance. They're about almost 500 to 1,000 times larger. It's quite a bit. The speed of light here, I thought this was really particularly interesting. So 5.169 inches per second, about that. So 1 1/3 is about how long it takes. 1 1/3 light seconds. 1 1/3 seconds for light to travel from the Earth to the moon. It's about that fast. So my finger is moving at the speed of light, just so you guys can see. Let's zoom in. I think it might be closer to that, something like that. So it's amazing. And it goes around the Earth 7 times in a second. 1, 2, 3, 4. I can't move that fast. And so if you can imagine my finger moving this fast, if I get my finger moving in a straight line that fast for 8 straight minutes, that would be about 8 minutes. That would be the distance between the Earth and the Sun. And what that is on our scale here is 215 feet, 214 feet. 8 minutes going that. It's like It's like downloading a song from Napster in 2001. That download time, watching that bar, the download bar is about how long it takes light to get from this sun 400 times larger than the Earth, 400 times wider than the Earth. Before we do the volume, I just wanted to say the light year. Light travels about 131 millimeters this far in a second. A light year is 2,500 miles. So the nearest star, roughly about 4 light years away, is 10,000 miles away. 10,000 miles, that's about, let's say, from Florida to somewhere in Asia. Mileage. Let's just look up the, radius of Earth. The radius of Earth is roughly 4,000 miles. Circumference. So if we let's do a little fact sheet for all these. Radius, 4,000 miles. Circumference is, and down here let's do pi r squared is the area 2 pi r. 2 pi times r, or 2r is d, so pi times the diameter. 2 pi times 4,000 miles. So pi times 8,000, 25,000 roughly miles. So, I'd have to go halfway around the Earth at this scale to be to go from our star. If it were this large, we have to go 10,000 miles away, almost halfway around the Earth, to get to Proxima Centauri, the nearest star. Mars, the radius of Mars. Let's see, Mars radius, 2,100,000 miles. So its circumference would be, let's see, 4,200 times 3.14, 13,000. We could see the difference. 13,200 roughly miles. So we could see it's roughly almost exactly half the circumference in radius. Okay. Alright, before we keep goofing off anymore, I just wanted to volume. Let's see. Where's the volume of the sun? 1.3 million Earths. So the sun is 400 times the diameter of the Earth. 400 of these little peppercorns would fit in our sun if we actually described it all the way out. But it's not 400 times the volume of the Earth. It's 1.3 million times the volume of the Earth. So that's a huge distinction. Earth versus sun. So the mass of the sun, 330,000 times the mass of the Earth. Okay. So the sun is, the Earth has the rocky planets. It's rocky. The Earth has an iron mantle, core. We have a lot denser elements in it, so it's 1.3 million of these would fit in our sun. But the sun is only, so it's 1.3 million times the volume of the Earth, but it's only 330,000 times the mass. Oh no. I keep wiping away the moon and the planets. Okay. Alright, let's go ahead and figure out the gas giants and place them. Let's see. Let's make nice little circles out of them. Oh, look at that. I didn't realize that was a hinge. Okay. Okay. Alright. So the first gas giant, Jupiter, let's see. Let's go back to our scale of the solar system. Jupiter is 2.46 inches in diameter, 62, we'll say 63 millimeters. Okay, does it fit? Just fits, look at that, in diameter. Okay, so let's mark that, 63, 63, so it'll be about right there, in diameter. Remember diameter, so that's the entire planet, not just the radius. Let's mark that, stamp it there, and do that. Oh yeah, what am I doing? As I was telling you guys that, so let's mark 31.5. Let's see, that'll be about that. About right there. Okay. So let's do. Is that gonna fit? Yeah, just gonna fit. Okay. So let's draw this. Oh, it's not gonna fit. Okay, let's try a different universe. Let's do a dry run first. Okay. Look at that. almost fits on a post-it note. That's pretty cool. So there's Jupiter. And then Saturn is still very large, but 50, so let's say 51 millimeters, 25.5. Just say 25 right there. Let's make it smaller. 25.5. It's getting the light a little better, I guess, for you guys. 25.5. Okay. Fantastic. Right there. And that's Saturn. But of course, Saturn's rings go out much further than that. Then Uranus and Neptune are considerably smaller, about half the size, less than half. So we have I guess I'll just measure it from here real quick. Uranus, 20 millimeters in diameter, so 10. Wow, it's actually way smaller than I realized. Look at that, it's a centimeter. It's like a centimeter. That's amazing. So roughly, yeah, let's get a little more accurate with that. Make sure, double check. Yeah, that's good enough. That's Uranus. Alright, commence jokes. And then Neptune, last of the recognized planets, is just a little bit smaller than that, so we'll just make that just a little bit smaller. Just about 9 millimeters, alright. Alright. I don't know where that came from. Okay, so let's get our scissors. Let's draw Neptune. Let's cut him out. Look at that. I did not realize Neptune's only that large relative to Earth. I honestly did not realize it was that small. I thought it was as large as a lot closer to Jupiter and Saturn. So we got Neptune there. On this planet. Okay. And there's Uranus. Or is this Uranus? Just kidding. Then we got Saturn. Much easier to cut, by the way. Much easier to cut. Saturn, 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 Saturn. Look at that. And then the largest, closest, and largest of the gas giants, the shepherd of the inner planets, shepherding with its gravitational field many asteroids, comets, meteors, away from the inner planets. Okay. Alright, look at that. So we have Mercury, Venus, Earth, Mars. And we got the gas giants. Jupiter, Saturn, Uranus, and Neptune out there. That's really cool. This website was created in 1997, and just because there was, maybe a couple hundred more fields that were being calculated, the guy actually warned that it might take a lot longer to load those calculations. Testament to the improvement in technology. I want to point out that the true distances, given that the sizes are accurate here, and the only accurate distance is actually the Earth to the Moon here, which is pretty incredible when you think about it. So the astronauts made a 3-day journey going to the Moon. That's just so incredible. In low Earth orbit, the ISS wouldn't even register on this scale. You'd have to maybe make the Earth as big as the Sun is right here, and then maybe low Earth orbit would be something like, maybe something like that right there. Well, my phone just died. Okay, so you guys can't see that anymore, but maybe like half an inch off the Sun. Mercury would be at this scale that we have here, and I'll just superimpose a previous image of this. Mercury would be 83 feet away from this 2-foot wide Sun. Venus would be 150 feet away. Earth just over 200 feet away. Mars would be quite a bit further, but still manageably, understandably close at 330 feet away. And Jupiter is starting to get pretty far away at 1,000 feet, 1,118 feet away. And then it's interesting that Mars's orbit is about twice the distance from Earth as Earth is from Venus, and Saturn's twice the distance from Jupiter as Jupiter is from the Sun. So it's pretty interesting, and then that this pattern emerges, and it has to do with orbital resonances. So many other planets that didn't neatly fall into these distances that are multiples of each other on average, probably would have either gotten swallowed by another planet or booted, gravitationally speaking, out of the solar system, maybe billions of years ago. So Saturn's 2,000 feet away. That's half a mile at this point. And then Uranus is 4,000 feet. On this scale, Uranus is almost a mile away. It's about 80% of a mile. And then Neptune is over a mile, almost a mile and a half away. Neptune would be almost a mile and a half away if our sun was only 2 feet in diameter, and our Earth was a peppercorn sitting 200 feet away from the sun. That's so far. Guys, I really hope this was useful for helping you, and it helped me. It really is actually really fun to practice these visualizations and fleshing out these concepts, specifically if anything else, like I said, the distance to the moon. I think it's really interesting, the true distance and proportions of the planet's sizes and the interplanetary distance between us. It takes light 20 minutes to get between Earth and Mars, for instance, which is about a little over 100 feet on our scale here. Let me know what you thought. Otherwise, I hope you had a good time. We'll see you next time.